component algebra of vectors where we expressed components with respect to xy coordinate plane or the two-dimensional plane, where we expressed the vector in I cap and j cap notation, or with respect to the two unit vectors I cap and j cap in the xy plane. Now today the next concept we will learn of vectors is the component representation in 3 dimensions. So component representation of vectors in 3D or 3 dimensions. Or you can say with respect to a 3-dimensional system. Okay, so let us understand more about this. So first of all, let us talk about a 3-dimensional rectangular coordinate frame. Or this is also sometimes called the Cartesian coordinate system. So this consists of 3 mutually perpendicular axes. Okay. X, Y and Z axis. So mutually perpendicular, this term what it means? It means that X axis is perpendicular to Y axis. X axis is also perpendicular to Z axis. Okay. And Y axis and Z axis are also perpendicular to each other. So Y axis is perpendicular to the Z axis. So any pair of axes among the three are mutually perpendicular with respect to each other. That is the meaning of the term mutually perpendicular. Okay. So just make a note of this first, then we will see how to draw this system of coordinates, and from there we will carry on further. So in order to understand component representations in 3D system, we need to understand what a 3D rectangular coordinate frame consists of. So it consists of the 3 mutually perpendicular axes x, y, z, okay, drawn from a common origin. So the system is defined by drawing 3 axes which are perpendicular to each other and all of them originating from a common point, which is called O. Okay, so if you finish writing this down, let's understand how to draw these axes. So a system of mutually perpendicular axes would look something like this. If we have to try and draw it in a 2-dimensional diagram, now you have to understand that this is not 2-dimensional, actually it's 3-dimensional. So this axis is perpendicular to this one, this is perpendicular to this, and this is perpendicular to this. So imagine this xy plane. So imagine the plane that is formed by these two axes. Just think of it like the wall in front of you. You're sitting in a room, so the wall that you're seeing straight in front of you, that wall is this plane that I've drawn over here. So the edge on the floor, which is right in front of you, that edge is the x-axis. The edge or the common edge between the two walls, which you see in the front corner, that one, that is the y-axis, and this one is the z-axis. So when you look to your side, on this side, you see another wall. When you look to this side, you see another wall. In front of you, you're seeing one wall. So in front of you, the wall that you're seeing, that's the XY plane. On your side, on this side, you're seeing another wall. That is the YZ plane. And the floor on which you're sitting, that is your ZX plane or XZ plane. So these are the three mutually perpendicular planes. So this is how to visualize the three-dimensional system. This is the ZX plane. Think of it like the floor on which you are sitting. Okay, and this one in front of you is the XY plane. So these are mutually perpendicular planes also. So think of this like the wall in front, the wall that you are facing as you sit in a room, and the wall to your side, that is your YZ plane. So this is the side wall. So then you'll understand what the system of axes is. And the corner of the room in front of you, on your front left, the bottom front left corner, that is the common origin. So another way to visualize this three-dimensional system is, instead of this, you visualize something like this. We have made a rectangular box. So take any one corner of the box, like your origin, and the three mutually perpendicular edges of the box become your X, Y, and Z axis. Okay. So just think of this like a cuboid or a rectangular box. So any face is perpendicular to the other face. Now within this rectangular box, you take any one corner as your origin and draw the axis along the edges. So this is your x-axis. This point is your origin. Correspondingly, this is your y-axis. And this would be our z-axis. That's another way to visualize the XYZ system. So this wall in front of you, this is the XY plane. This floor on which you are sitting, this is the XZ or ZX plane. And this wall to this side of you, this is again the YZ plane. So this is your system of mutually perpendicular axes. X is perpendicular to Y, Y is perpendicular to Z, and Z is perpendicular to X. So this is the first thing we have to learn, that we have to understand how to visualize the three-dimensional coordinate frame. Okay, so that then we can visualize vectors in them, because the vector could lie in any direction, doesn't have to lie in any particular plane. So the best way to visualize is in the three-dimensional space of the room in which you are sitting. So take the three edges from one corner of the room to be your mutually perpendicular axis. So then the three planes formed by those edges, the floor on which you are sitting, the wall in front of you, and the wall to the side of you. The wall to your side, the wall in front of you, and the floor on which you are sitting. Now these are your mutually perpendicular axis. So to one side of you, you have a wall. To in front of you, you have a wall. So these are two mutually perpendicular planes like this. And then the floor on which you are sitting, that one. So those are your three mutually perpendicular planes formed by the mutually perpendicular axis. So hope this part is clear to all of you. Okay. Now next, once you've defined your coordinate axis and the origin, next what we do is we define the base unit vectors like we've done for two-dimensional system. But only now we have three of them. Base unit vectors or the standard vectors, we have three of them, I cap and j cap. What they were before, same thing here also. But now we have one more, which is k cap. So these are the unit vectors along x-axis. Then this is a unit vector along the y-axis, and this becomes the unit vector along the z-axis. So these are the mutually perpendicular unit vectors. So in this diagram, for example, how would these unit vectors look like? This is I cap, a vector of magnitude 1 along the x-axis. Okay. This would be j cap, and this would be k cap. Okay. Or strictly speaking, if we look in a two-dimensional system, this is your x-axis, this is your y-axis. So if we look at it this way, then I cap is the unit vector like this, j cap is the unit vector like this, okay. And k cap, you would just see the tip of the arrow coming out towards you. So k cap would be a unit vector coming straight out, okay, of the xy plane. So that's how we visualize this. Okay, so hope you finished writing this down. Now we come to the vector part. Okay, once you've defined the coordinate frame, so this is about geometry actually. So you three-dimensional geometry. So now about the vector. So any vector, say A, in the three-dimensional system will be expressed as the sum of three mutually perpendicular components, ax I cap plus ay j cap plus az k cap, where as usual ax, ay and az are scalars. Okay. They can be positive or negative, as may be the case. Okay. Called the x component, the y component, and the z component of the vector E. And of course, we know what I cap, j cap, and k cap are. Okay, so let's learn to visualize how this vector looks with respect to our three-dimensional system. So let's take an example. Suppose we have this vector which is, say, 3 I cap plus 4 j cap plus 2 k cap. Now let's understand how to visualize the vector in the 3D coordinate frame. So next step we are going to do that. So imagine we have drawn our three axes, the mutually perpendicular x, y, and z axis, like this. These are a system of axes, is the common origin. Okay. Now just think of what this vector is. 3 I cap. It is a vector of magnitude 3 along the x axis. So in my diagram over here, I would represent it, I could represent it by just drawing this. So if this vector is 3 I cap, okay, then I could say that it points from the origin to a point A, where the coordinates of the point A are 3, comma 0, comma 0. So this could be a vector from O to A. So that 3 I cap is the vector OA in my diagram, where the origin is obviously having coordinates 0, 0, 0, and the point A is having coordinates 3, comma 0, comma 0. Now likewise you can understand what is the vector 4j cap. It is a vector along the y-axis, or you could say that 4j cap is like a vector OB, where the point B is 0, comma 4, comma 0. So if you take a point on the y-axis over here, इसके coordinates क्या है 0, y coordinate 4 and z coordinate 4 again, then you could easily say that okay, the vector 4j cap is nothing but the vector joining the origin with this. Okay, so this is OB. And similarly, if I take another point now here on the z axis, this point let's say C. Now this point is having coordinates let's say 0, 0, 2. Then this vector here joining O and C, ये वेक्टर अब क्या रिप्रेजेंट करेगा? This will represent 2k cap, whereas this vector was representing 4j cap. Okay. So likewise, 2k cap is a vector along the z axis. So in my diagram, I'm representing that 2k cap as the vector OC from the origin to the point C, where C's coordinates are 0, 0, 2. Okay. Now, in comparison to all this, what is my vector A? My vector A itself is the sum of these. My vector A is the sum of 3 I cap, which I have shown here as this vector, plus 4j cap, which I have shown as the vector OB, plus 2k cap, which I have shown as the vector OC. So how will that vector look? Okay, so first make a note of this diagram. Then we'll proceed how to add these three vectors in that three-dimensional space, okay, and understand what that vector is looking like. Alright, so we have written this down. Now let's understand what this vector looks like, which is the sum of all this. How we will draw this one. So just to visualize this vector, you can do something very simple, and that is that we can now use that example of that rectangular box that we were talking about earlier. We can use that as a tool, or that as a method of visualization. So just imagine you have this okay. Only that it's a bit specific now, that its edges are of specific lengths. So its edges are of specific lengths, let's say 3, 4, and 2. So now what I will do is I will select this as my origin. Okay, and accordingly I will select my system of axes. This is my x-axis, this is my y-axis, and this is my z-axis. So in context of the previous diagram that we had made, this point is A, whose coordinates are 0, 3, 0. This point is B, whose coordinates are 0, 4, 0. And this point here is C, whose coordinates are 0, 0, 2. Okay. But then additionally, I could also say this point here, let's say D, is 4, sorry, my mistake. First of all, this is on the x-axis. So this one's coordinates are, x coordinate is 3, y and z are 0. So this is 3, 4, 0. And this point here, this corner, is E, which is 3, 4, 2 with respect to this origin. Okay. So now let us see where my vectors lie in this diagram. So in this diagram now, my vector 3 I cap starting from the origin is this one. Okay. But now see, what I want to do is, to 3 I cap I want to add 4 j cap. मेरे को 4 j cap add करना है. So I will not place 4 j cap over here. I will think of it like, like we did for addition of displacements. So I'm doing the displacement of 3 I cap. So I'm reaching the point A, and then from the point A I'm making the displacement 4 j cap. So which should be my 4 j cap? It should be drawn from A instead of from the origin. So that will bring me to the point D. So this is 4 j cap. Okay, and then 3 I cap plus 4 j cap plus another displacement I'm adding, 2 k cap. So that will bring me from the point D to the point E. So my third component I'm adding to the first two will add from D and bring me to this point E over here, as you can see. So this will be my 2k cap. So I'm starting from the origin, and after completing the displacement of 3 I cap plus 4 j cap plus 2k cap, where I'm reaching? I'm reaching the point E. So in all of this, what is my resultant vector, which is A, which is the sum of all these three? It is nothing but from my initial point O to my final point E. So this is becoming the vector that I was looking for in the first place. This is the vector E, which is given by this equation. So you can see, as far as the visualization is concerned, visualization of the vector E, it is the body diagonal, that is the diagonal going through the body. Okay, in this case the body diagonal OE of the cuboid with sides OE equal to 3 I cap, AD equal to 4 j cap, and DE equal to 2k cap. Okay. this kind of situation where, okay, where O is the point with coordinate 0 comma 0 comma 0, and E is the point with the coordinates x comma y comma whatever the z is. So in this case they are 3 4. So this is the visualization. So again, the room in which you are sitting, just imagine the body diagonal going from the origin corner in front of you, to your bottom left in front of you, to the corner behind you, which is, so the diagonal cutting through the body of the room, the rectangular room in which you are sitting. That is the vector OE. I mean, that is the vector E, which is nothing but the vector joining the corners O and E. Okay. So this is the easiest way to visualize this vector. So make a note of this also. So this is how we visualize in three-dimensional system. Okay, so if you're thinking about an object making a displacement of 3 I cap plus 4 j cap plus 2 k cap, you can understand that the displacement vector is just the body diagonal of that room. And the object has moved from one corner of the room to the I mean, to the diagonally opposite vertex or corner, such that it is cutting through the room through a body diagonal. So, that is how you understand how vectors can be placed in three dimensions, or how displacements, velocities, accelerations, all these three can work in three dimensions. So in reality, in the physical world around us, most things are moving around in three-dimensional space. It's only in special cases that objects are moving on two-dimensional planes. Like yes, when we are moving around on a room, or we are driving a vehicle on a road, most often we are on the two-dimensional plane, unless we are going up a hill or something. But we are on a two-dimensional plane. But any insect flying around in a room, or the motion of a helicopter or an aeroplane, or any such thing which is not lying two-dimensional flat plane, okay, that kind of motion immediately becomes three-dimensional. Yeah, so Rupesh, to answer your question, in geometrical space there is no such thing as four dimensions and five dimensions. Okay. In relativistic space in physics, for gravitation and all that, that is relativistic dynamics, which is like a little bit advanced physics. There is some such notion as four dimensionality. The three x y z coordinate frame plus the axis of time. So time becomes like a fourth dimension. But we don't really have to worry about that right now, because we are dealing with mechanics and not relativity. And in mechanics, everything will be restricted to three dimensions. So whether we are talking about something very simple like like an object rolling down an inclined plane, or a, a pulley system, or a block and tackle system, or anything like that, or something more complex like the motion of a rocket or a satellite or something like that, or even the motion of electrons inside an atom, dealing with three-dimensional systems only. Okay, so unless you take up a course at the graduate level which deals with relativistic physics, you will not be dealing with four-dimensional system where time is a separate axis. You'll always think of time as a separate physical quantity, nothing to do with your coordinate axis. And the motion or displacement or velocity or whatever is always with respect to the XYZ system, or the three-dimensional coordinate frame. Okay. So in other words, for us the maximum is 3 dimensions, and for most of engineering and technology the maximum is 3 dimensions. It's only in higher physics that you deal with the fourth dimension of time. Okay. All right, now about the properties of 3D vectors. Okay, Ketan, I'll give you some time. Okay, very good. Now about three-dimensional vectors. So first thing is that if the vector A in component form is expressed as ax I cap plus ay j cap plus ez k cap, then the magnitude of the vector E is given by this formula. It is square root of the sum of the squares of the three components. This. Okay. Now this is very easy to understand. Think of it like B plus C, where B is the vector ax I cap plus ay j cap. Okay. So magnitude of B is root of ax square plus ay square, and C is the vector az k cap. Okay. So if we are defining B and C like this, now the interesting thing you can see is that B is perpendicular to C, because B is lying in the xy plane, okay, and C is along the z axis. So mod of A should be equal to mod of B plus C, and they are perpendicular to each other. These two vectors are perpendicular to each other. So that will become square root of magnitude of B square plus magnitude of C square. So magnitude of B is that, and magnitude of C is this. So it is square root of ax square plus ay square, that's B's magnitude whole square plus C's magnitude whole square. So naturally it becomes square root of ax square plus ay square plus ez square. So this is one way of understanding why the magnitude should be given by this sort of an expression. Okay. So basically you can just break the vector into the sum of two other vectors. So you these two together you take as the vector B, and this one you take as the vector C. So they are perpendicular to each other. They are perpendicular vectors. Okay. So magnitude of B plus C becoming square root of B square plus C square, and then you just substitute this. So that's how you see you get that equation. So there's nothing complicated about this equation. It's very easy to understand from this. No, it's the formula which is important for you. At the end of the day, it's only the formula which is important. This this part is just for you to understand. It's this formula which is important. So, for example, if I have a vector, say 2I cap plus square root of 2j cap minus square root of 2k cap, then the magnitude of the vector will become square root of 2 square plus root 2 square plus root 2 square, so it will become 4 plus 2 plus 2, so that is 2. So, then so let's look at an example problem where we have to apply the concept of three-dimensional vectors. Okay. So in this example problem, a particle makes a displacement S1, let's say, of say 12 meters towards east. Okay. Then another displacement S2 of, let us say, 15 meters at 37 degrees west of north. Okay. And finally, a vertical displacement of 10 meters, that is, let's say, S3. Find the magnitude of its net displacement, which is nothing but the vector sum of these three displacements. So just try this out, people. So what I would advise you to try in this question is that express S1, S2, and S3 in component form. So what you do to solve this question is, first of all, make an XYZ system is that x-axis is pointing towards east, y-axis is pointing towards north, and z-axis is vertical. Okay. So you can see that the xy plane is the horizontal plane. Okay. The plane of the ground, and this is the vertical. Okay. So that's the first step. Then express S1, S2, and S3 in component form. That's the second step to do. And then add them. So then you'll be able to solve the problem by the time you come to the third step. So just try this out according to this method. right? So anybody reached up to the first step, S1, S2, and S3 in I cap J cap form? So if you've written them in I cap J cap form, just send it to me in the text message, and let me try and explain that concept further by using a diagram. So suppose this is a horizontal plane, the surface of the table on which you're writing, or the floor on which you're sitting. So this is the horizontal plane, like this. And within this plane, I'll just check your answers, just give me a second. This is the axis pointing towards north, and this is the axis pointing towards east. So this is your south to north direction, and this is your east to west, sorry, west to east direction. So we will define this as our x-axis, and we'll define this as a y-axis. Okay. And in comparison to this now, this will become our vertical axis, this one. So this will become our z-axis, which is vertical. So vertical means it is perpendicular to the horizontal plane, or another easy way to understand vertical is its opposite, gravity. Okay. This is your acceleration due to gravity. So this is how our system of coordinates should look like. Okay, then the first and third are correct, but the second one is a little bit more complicated. Okay. So now if we just look in the xy system, so this is east, this is the north direction, okay, and this is the west direction. So how is the vector S1 looking? It is like this. S1 is a displacement towards the east of 12 meters. So S1 should be 12 I cap. But in comparison to this, how is S2 looking? Now S2 was a little complicated. S2 was like this. It was at 37 degrees west of north. ऐसा था ना? And it was 15 meters in length. This was S2. So how will S2 look in component form? We'll have an X component of -9 and a Y component of +12. This is what our vector S2 will look at, because our vector S2 is like this. This total angle is 127 degrees. This is 15 meters. So from component algebra it will look like this. But as far as the third vector is concerned, that we cannot show in this diagram, that we can show in the three-dimensional diagram. That's like this. S3 is a vertical displacement of 10 meters. So S3 कैसा होगा? It will be 10 k cap, vertical of this much. So these are the three vectors, the individual displacements S1, S2, and S3 written in component form. Hope this is clear to all of you. You just verify the results from the angles and everything also. Only the second one you need to check. I'm sure the first and third are clear to all of you. So this is like the practical application, how we can make use of three-dimensional coordinate system to understand motion or displacement in this case. Yeah, S2, Kirtan, from the language you'll understand, S2 was making an angle of 37 degrees west of north. So north से west की तरफ मुझे कितना मुड़ना है 37 degrees से. Understood? Yeah, Uday, I'm explaining the same. So just concentrate on the diagram, the vector S2 that I made, the arrow, उसका direction कैसा होना चाहिए 37 degrees west of north. That means मुझे west, I mean मुझे north की तरफ से turn करना चाहिए towards west, but by how much angle? 37 degrees. Got it? Understood how the arrow is drawn? Uday and Kirtan, is this clear how the arrow is drawn? Okay. So now you see that angle is 37. So that means with my x-axis, how much is the angle? The angle is in the second diagram. It's 127 degrees. It's 90 plus 37. So magnitude is 15 and the angle is 127. So x component कितना हो जाएगा? 15 cos 127. So when you work that out, that will come out to be minus 9. And y component कितना हो जाएगा? 15 sin 127. So when you work that out, that will come out to be 12 plus 12. So that's how I've written it as minus 9 I cap plus 12 j cap. And that process is called resolving a vector into components. Right, so that is just two-dimensional resolution like we've been doing all along, no? In the xy plane, if the angle with the x-axis is theta, whether that's first quadrant, second quadrant, doesn't matter, we just have to use the trigonometric formula. So magnitude into cos theta is the x component and magnitude into sin theta is the y component. So when you write 15 into cos 127, when you solve that, automatically you get minus 9, and 15 into sin 127, automatically you get plus 12. Uday, it is clear now how we wrote S2? Okay, very good. Good. So now what we have to do, we have to just add these three vectors. So we've got the three vectors in individual component form. So now our net displacement, this is nothing but the vector sum of S1 plus S2 plus S3. So just substitute these. So 12 I cap, that is my S1, plus minus 9 I cap plus 12 J cap, that is my S2, and plus 10 K cap, that is my S3. Now next, just normal algebra, just open these brackets. So take I cap common. So you have 12 minus 9 I cap plus only one J cap term. So that's 12 J cap plus only one K cap term. So that's this. So your resultant displacement in component form is 3 I cap plus 12 J cap plus 10 K cap in meters. Each of these are in meters. So this is the net displacement in component form. Now we have to find its magnitude. So just use the formula of magnitude. The magnitude of a three-dimensional vector is of x component square plus y component square plus z component square. So in this case, it's 9 plus 144 plus 100. So that becomes square root of 253 meters. Okay. So we can leave the answer this way only, or we can simplify it a little and approximate it. So it will be 15 point something. Let's work it out. Yeah, it will be close to 16 actually. 15.9 approximately. So that is our resultant displacement. So as you can see, this is pretty easy. Okay, so that is about your three-dimensional vectors. As a quick example, we'll just do one more question. So let's say P is I cap plus 2j cap minus k cap. Q is 4i cap plus 3j cap plus 10k cap, and is R is 2i cap plus j cap, okay, and minus 3k cap. So we want to find P plus Q minus R and the magnitude of the same thing, P plus Q minus R. So very simple question. We have to just apply the normal principles of algebra. Okay. So you can just apply this kind of principle that in component form, A plus B becomes the sum of the x components into I cap plus the sum of the y components into j cap plus the sum of the z components into k cap. And similarly, if we are subtracting two vectors, let's say d minus e, in component form it becomes the difference of the x components plus the difference of the y components plus the difference of the z components. Is basically you just write d and e in component form and then take I cap, j cap, k cap common. Similarly, you write a and b in component form and then express that resultant sum after taking I cap common. So you'll get these two terms ax plus bx with I cap. Similarly, take j cap common. So it's not really a separate formula, it is just the application of addition. So anybody got the answer yet? Yes, very good, Uday. That's correct. Now just find its magnitude. Okay. So, no, Kirtan, you have to check your answer again. So let's do the first part. P plus Q minus R. So I'll just express each of the vectors in component form. Minus K cap plus the vector Q, which is 4i 3j cap plus 10k cap, minus the vector R, which is 2i cap plus j cap minus 3k cap. So this is the operation. Now take I cap common. So we have 1 plus 4 and then minus 2. Then take j cap common. So we have 2 plus 3 minus 1. And take k cap common. So we have minus 1 plus 10. And then again this becomes minus minus plus 3. So you have to just be a little alert while doing the algebra. Rest of the things are simple. So what we get is 3 I cap plus 4j cap plus 12k cap. So this is the vector that I was looking for. P plus Q plus, sorry, P plus Q minus R. So this is the answer to the first part. Okay, now the second part I have to just find the magnitude of this thing. So this is the first part. And the second part I have to just find magnitude of P plus Q minus R. So that is nothing but magnitude of this vector, 3i cap plus 4j cap plus 12k cap, which is square root of 3 square plus 4 square plus 12 square. So that will be square root of 9 plus 16 plus 144. So that when you work out is square root of 169, which is nothing but 13. So it's extremely simple number that we come to at the end of the day. So mod of P plus Q minus R comes out to be this answer. So this is your second part's answer. Yes. So hope it is now clear, Kirtan. Okay. So it's very simple. It's just like you have to be careful not to make any careless mistake while solving. That's all. There's nothing difficult in this because you're already used to the two-dimensional vector algebra. So in three dimensions, just the k cap component is getting added. Okay. Otherwise, it's exactly the same type of operations. So nothing new over here. So hope you are all clear with this. Oh, good. So so now we are done with the major part of vectors. because in the coming few chapters in physics we will be using all these things: addition of vectors, subtraction of vectors, component algebra, parallelogram law, geometrical interpretation, all these things. Okay, but now that all that is done, we come to the last part of vectors, which is to do with a new type of operation of products. Now these operations we won't be using immediately right now in physics. We'll be using them 2 or 3 chapters later, in chapters like work energy theorem, and then later in rotational mechanics, etc. Okay, but nonetheless they are important to understand also. So the next part of vectors we'll study is something called a new type of operation for us called the dot product. Okay, of vectors. So this is also called, also known as scalar product. Now, just because the term product is used, you should not confuse it with multiplication. This is a totally new operation for us, and it has not really anything to do with multiplication of numbers like we know, like 2 into 3 is 6 and 4 into 5 is 20. It's not something like that at all. It's related to vectors. So the operation symbol is this. The symbol for this operation is, if we put a dot in between two vectors, then it is read as dot product, or we can also call it scalar product of vectors A and B. So that's just the symbol, nothing big about that. Now, what is the definition? This is the main thing. How do we define this operation? So, this operation, as I told you, is something completely new for us. It is given by this definition, that it's A multiplied by B in terms of components, or rather magnitudes, into cos theta. So, this is the formula or the definition of the operation, that calculating the dot product results in this operation. You multiply the magnitude of A with the magnitude of B with cosine of the angle between A and B. So theta here is the angle between vectors A and B. It's as simple as that. Okay. So as a simple example, suppose we have two vectors which are shown to us like this. Say this is vector E. It has a magnitude of 10, and this is vector B, and it has a magnitude of, let's say, 12, and the angle between them is 60 degrees. So then A dot B, so here A dot B will become magnitude of A into B into cos theta. So that will become 10 into 12 into cos 60, which you can see will become 60. So it will become 10 into 12 into half. So that's 10 into 6, or 120 into half, or 60. And the other thing is, if this is expressed in some unit, and this is also expressed in the same unit, then this will become 60 units square. X. So just write down the definition, then we'll understand more about it. Right. So hope the definition is clear. People, I'll just take a few minutes extra today. I'll leave the class before 8:30, Kunwai, but I just want to complete the definition of dot product so that we can get started on this. Unfortunately, we had a delayed start because of internet connection issues at my end. So I'll just take something like 10-12 minutes extra, finish before 8:30. Now let's look at another example. If vector E is like this and vector B is like this, they're of magnitudes 6 units and 8 units respectively, but they're like this. With respect to the xy plane, so vector E is making an angle of 30 degrees here and B is at a symmetrical angle of 30 degrees here. So now I want to find out A dot B. So just use this formula that you can see right above here. Use this formula here, but instead of those values, use these values now in this question. Yes, anybody got the answer? Very good. That's correct, Vijay. Vivek, there's a minus sign involved, because cos 120, So the main thing is what is the angle between these two vectors? That is this angle. So that theta you can see is 120 degrees, and magnitude of A you can see is 6 units. Magnitude of B you can see is 8 units. So cos theta is cos 120, which you know is minus cos 60. So it's in fact minus half. So therefore A dot B will become 6 units into 8 units into minus half. Okay. So it's minus 24, whatever unit squared. So the correct answer is with the minus sign. So this is an important aspect of dot product. Okay. Dot product can have a negative value. It's a scalar quantity but with algebraic sign plus or minus. So that brings us to this property. So from this definition, A dot B is a scalar. Okay. Secondly, A dot B is equal to a positive quantity if theta is acute. It is 0 if theta is 90 degrees. And it is negative if theta is obtuse. So it can be a scalar which is either positive, negative, or 0 according to the angle. So that's the important thing. Okay. Now, this will also explain the next property I'm showing. This will be magnitude of A square because A dot A will be A into cos 0. So cos 0 is 1. So that is A square. Okay. And the next property I'm showing you is self-explanatory, that A dot B is equal to B dot A. This is called the commutative property because A dot B is AB cos theta by definition, and B dot A is BA cos theta, which are equal. No difference between the two. Okay. And the final one, if we take dot product of A with the sum of two other vectors, then we can express it as the dot product with the first one plus the dot product with the second one. So this one is called the distributive property. Okay. So dot product is both commutative as well as distributive. Okay. So make sure you understood all these points here. Now the final thing about dot products. So dot product in component form. So when we are writing this, keep in mind that I cap dot I cap is 1, j cap dot j cap is 1, and k cap dot k cap is 1. This directly comes from the property we had understood that if you take dot product of a vector with itself, It gives you square of its magnitude, and I cap and j cap and k cap have a magnitude of 1. They are unit vectors. However, if you take I cap dot j cap, that will give you 0, because E dot B is equal to 0 if they are perpendicular to each other. So this is another thing. Similarly, j dot k is 0, and say k cap dot I cap will be 0. So once we understand these properties, it's very easy to understand how to work out dot product in component form. So therefore, if for example vector A is Ax I cap plus Ay j cap, and vector B is Bx I cap plus By j cap, then when we write A dot B, we can just use the combination of these formulae above and also the distributive property. So just express A and B in their component notation, and then expand this operation using the distributive property. So this will become Ax into Bx multiplied with I cap dot I cap. And the first term is dot product with this first term. Then it will become Ax into By, but dot product of I cap dot J cap. Then it will become Ay into Bx dot product of J cap with I cap. And finally one more term, Ay into By dot product of j cap with j cap. Now in this you know that these two terms will be 0 because of this relation. Okay. Whereas these two terms, this is 1 and this term is 1 because of these relations. So finally what I'm left with, I'm just left with Ax into Bx plus Ay into By. So this becomes a formula for dot product of two vectors when they are in two-dimensional component form. So this is for 2D component form. So it's just a very simple formula when it reduces to this. So for example, if we have a situation where vector A is, let's say, 2 I cap plus 3 j cap, and vector B is, let us say, 4 I cap minus j cap, then we want to find out A dot B, how much that is. So you just use this formula. A dot B is Ax into Bx plus Ay into By. So that is in this case 2 into 4 plus 3 into minus 1, so that is 8 minus 3 or 5. So our A dot B is a very simple answer here, it's just equal to 5. So this is how we find dot product in component form in the two-dimensional case. Now we'll just expand this to 3D also, but first we note down this. Okay, so Please let me know if you have any doubt with this part. Okay, so the final thing for dot products is in 3D, in three-dimensional component form. The formula just becomes an extension of what we have written in 2D. Ax into bx plus ay into by plus now the product of the z components. And the logic of this formula is very similar. If you write the three vectors in three-dimensional form and then take the dot product and eliminate the terms which are 0, keep the terms which are 1, you will get this formula very easily. So this is the 3D form for dot product. So the simple example, if my vector A is, let's say, 3 I cap plus j cap minus k cap, and my vector B is I cap plus 2 j cap plus k cap, then A dot B, so A dot B here will just become 3 into 1, that is Ax into Bx, plus 1 into 2, that is Ay By, plus minus 1 into 1, that is Az Bz. So 3 plus 2 minus 1, that is 4. So that becomes the answer. Alright, so hope this is clear, people, and with this we will conclude today's session. So visualization of three-dimensional vectors as well as the new operation of dot product, two important things we've learned today. So make sure you revise this from the session recording and notes which I'll send. And I'll also send you a worksheet with some questions related to dot product application. So please try those questions out before our next lecture. And remind you that our next lecture is on Sunday. And in that we will learn the last of the vector operations, which is called cross products. So we are looking to wind up vectors now within a week or so. So please work accordingly and also try and complete maximum questions from the module exercises. Okay, we will keep one last session for discussion of doubts also from that, but start working on those questions already. Okay, people, so hope this is all clear to you. That's it for today's session. Wish you all the best.